Welcome back. In our first unit, we talked about how some problems can be solved efficiently in polynomial time, while others seem to require an exponential amount of exhaustive search. In this unit, we're going to talk about several of the classic strategies for polynomial time algorithms, and for each one we'll try to understand what is it about the structure of the problem that lets this strategy succeed or fail. We'll find out that each strategy relies on the problem having certain mathematical properties. Some problems give us the kind of insight that lets us solve them efficiently using one of these strategies. Some of them we really don't know how to handle, and those are the ones that we need some kind of exhaustive search. We're going to start by revisiting this idea of divide and conquer. We saw this before in the Towers of Hanoi puzzle. Now we're going to use it to solve a classic computational problem. It's not the most earth-shakingly fascinating problem in the world, but it's a classic and it probably uses up much of the world's computational resources, namely sorting. Sorting a list of n numbers from smallest to largest. Now, of course, this is something we do all the time in databases, dictionaries, whatever. But when you think about it, even sorting you could think of as finding the one good solution in a vast space of possibilities. In particular, if you have n numbers, there are n factorial different ways in which they could be ordered, and only one of these goes from smallest to largest. So if you'd never thought about it before, you might think that sorting was hard. Well, of course, sorting isn't that hard. But how can we sort numbers efficiently? I'm going to show you a particular algorithm called merge sort, which uses the divide and conquer technique. Here's how it works. In order to sort a list of 8 numbers, for instance, it will divide it into the left half and the right half. And then we're going to sort each of these halves. Well, now, how do we do that recursively? Well, remember how in the Towers of Hanoi puzzle, we broke the puzzle down into smaller puzzles of the same type, broke those down into yet smaller puzzles, and so on, until we reached a base case in which there was no work to do. In the Towers of Hanoi, it was that moving 0 disks takes 0 moves. In this case, after we break this list down into halves and then quarters and then eighths, eventually we get down to lists of size 1, for which nothing needs to be done because a list of length 1 is already sorted. So after we recursively sort these two halves, we then need to combine the results using a kind of merging operation. This kind of zippers the two halves together by repeatedly asking, should I take the next number from the bottom of this list or from the bottom of this list? And that requires us about n times to ask which of these two things is smaller. Good, so the lesson here is that if we sort the two halves, there's just a relatively small amount of additional work we need to do to get the sorted form of the entire list. Good. Now, in the Towers of Hanoi, we were able to exactly analyze how many moves it takes to solve the n-disk example of the puzzle. In this case, let's figure out exactly how much time it takes to sort a list of size n. Now, I'm actually going to count, instead of the amount of time, the number of comparisons, the number of times that the algorithm asks, which of these two things is bigger and which is smaller. So we're going to write down an equation for that, just as we had an equation for the number of moves that the Towers of Hanoi puzzle takes. There is a base case, so t of 1, the number of comparisons it takes to sort a list of length 1, is 0, no work to be done. And then there's this recurrence relation, which uses the recursive structure of the algorithm to turn that into an equation. So in order to sort a list of length n, we have to sort 2 lists of length n over 2, and then do this additional n comparisons to zipper the two together. It's actually at most n, so this might be a little bit of an overestimate, but that doesn't matter. So this tells us that t of n is twice t of n over 2 plus n. Now, we can use this equation, starting with that base case, to compute t of n for the first few values of n. And let's assume here that n is always a power of 2. I don't want to deal with the issue that maybe n doesn't divide evenly into 2 halves, or that the 2 halves don't divide evenly into quarters, and so on. So let's assume n is just a power of 2, so that we're always dividing it cleanly as we go down the levels of the algorithm. So this tells us, for instance, that to sort a list of length 8 takes a total of 24 comparisons.